ladies and gentlemen. My name's Sean, and today I'd like to do an example using the maximum shear stress criterion. So, for this example, we're going to be working with a member with a Young's modulus of 80 gigapascals, a Poisson's ratio of 0.21, and it's subjected to plane strain, where strain ZZ equals strain ZX, which equals strain ZY, which equals 0, when design loads are applied. At critical point, three of the stress components are sigma ZZ, or sigma XX equals 90 megapascals, sigma YY equals 200 megapascals, and sigma XY equals negative 120 megapascals. The material has a yield stress of 650 megapascals. What's the factor of safety using maximum stress criterion, shear stress criterion? So here's how we start this off. First, we use the strain, strain ZZ equals 1 over Young's modulus times the stress ZZ minus Poisson's ratio times stress XX minus Poisson's ratio times stress YY. And yeah, from this, when we plug in values, we get 0 equals 1 over 80,000. Note I use 80,000 because we're working this out in megapascals and E is given in gigapascals. And then, so stress ZZ minus 0.21 times 90 minus 0.21 times 200. When we solve this out, we get a sigma ZZ of 60.9 megapascals. And we also make that equal to our second principal stress. So then, when I write this out, all of these in a matrix, the stresses, I get 90 here, negative 120 for the x, y, and y axes, and then zeros for xz, zeros for yz, 60.9 for zz, and 200 for yy. And these are all in megapascals. So when we're next, we have to find sigma max and sigma min. So in the xy plane, sigma max and min are equal to sigma xx plus sigma yy over 2, which is then equal to the square root of sigma xx minus sigma yy over 2 squared plus sigma xy squared. Okay. So when we start plugging in values, we get 90 plus 200 over 2, then plus or minus the square root of 90 minus 200 over 2 squared plus negative 120 squared, and that simplifies out to 277, sorry, please ignore that, 0.004, comma, 12.996 megapascals. Sigma 1 equals 277.004 then, because we take sigma 1 to be the larger value. We take sigma 2 to be the value we calculated before for sigma ZZ, which is 60.9 megapascals. And we take sigma 3 to be equal to 12.996 megapascals, which is our minimum value. And then next we have to find tau max, so our shear max, and that is equal to our first principal stress minus our third principal stress divided by 2, which is equal to positive 277.004 minus 12.996 divided by 2, which ends up equaling 132.004 megapascals. Finally, we can take that value, our shear max, and make it equal to the yield stress, which is sigma yp, divided by 2 over n being the factor of safety. Then we can isolate for n, which would equal sigma yp times, divided by 2 tau max, which then equals 650 divided by 2 times 132.004, and we get a final n value, the final value for the shear stress of 2.462. Thank you, ladies and gentlemen, for your time. I hope this video helps you in understanding the concept better. Have a wonderful day.